Hey everyone, sorry this took so long. I was waiting for her to get a key up. She has not. Um, so so the first two questions I'm a little unsure about. So I'm gonna just start with the ones that I'm quite certain on, which is 3. So here we have a centrifuge, right? It gives you the radius of this. Gives you the radius, which you actually don't need, and then the angular velocity. Note that here the angular velocity is a function of time, which means that you're going to be doing the derivative. So time, it's a function of time, so you want the instantaneous velocity. I probably spelled that wrong, but bear with me. All right, so instantaneous velocity is, if you remember back from linear motion, you have acceleration is the derivative of velocity over time. You just turn that into angular motion, so alpha is equal to omega over time. So then from here, you have the derivative, right? And then we do the normal thing where we do the 1 minus 1, bring it down, minus the 1, bring it down, minus the 1. This t0 becomes a 1. These two multiply together, and that gets you your alpha, which I think I wrote it here. And then from there, then plug in time. Time. And then that gives you your instantaneous angular acceleration at that time. Okay. And the reason you do this is because you have this time here, so you can get accelerations as a function of t, and that way it's more precise than if you did the average. Cool. Cool. I'm gonna go ahead and clear these. Don't know if I want to take a photo. I'm gonna take a photo. Then we have this torque problem. This one's actually pretty easy. Because notice that this F is 5 newtons and this one's also 5 newtons. So they're the same. They're also at the same angle. So it's very symmetrical. That's just something that you want to note. This f of x here, keep it orange. This one's not going to matter because this is your axis of rotation. This one's not going to matter because there's no lever arm. This one's not going to matter. There's no lever arm. This one is going right with, going like this. So that one's not going to matter. So then only these matter. The Fy. And then because they're the exact same value, you just set the torques equal to each other. This d is distance. And that's force W. You don't know that this is 0 yet because it could be moving or could not be. But because these are exactly the same, then it means it's going to equal to 0. And that gives you your answer, where total torque is equal to 0. Then you have the bonus question. They give you the inertia of the uniform rod. I drew a little photo here where you see it rolling down. So you've got rotation here. So let's see. I don't know the translation, but you have in this case, the kinetic motion is seen by like it falling down the hill slope kind of. So then you can do, there we go. Did I use kinetic? I don't know if I did. But if you wanted to do this with energy, you probably could have. But so this is the force diagram of the forces, where this is the axis of rotation, right? Because if we use the axis of rotation, then the force friction is the only one with the lever arm. So if this is your axis of rotation, then F of N and F of G doesn't matter because no lever arm, right? So then you just have torque of force friction, where the R is this radius, right? R, that's your distance. And then by definition of torque, you do this I alpha. From there, you can solve for it. Right, by plugging it in, you have your I, which was given to you. You can solve for alpha using tangential acceleration. This is just an equation that you knew or should have known. And then this is again an equation that you should have known. So plug that in. You divide by R to get rid of this R. That gives you this. And you can plug that into there, which gets you this. You can divide out the R's. These cancel out from the A tangent. And then this is from the I. Which you can divide the R's there. And you already have one gotten rid of there. That gets you this. You just isolate, move stuff around. That gets you your A tangent. But you still have two unknowns. You have this theta and you have this mu. I don't think I finished solving for this one. But you can then take this A tangent and plug it into this equation. Solve for mu or cancel it out. I don't think you actually had to solve it because there's a lot of things that were not known. So this is just your answer here. A tangent is equal to this. Or you could have done this. Alright, so with that, we go back to the first two, which ignore my work for the first one. This, I've said it was symmetrical, but it's actually not, because these are two different masses. So it's actually going to look more like this. The x's should still cancel out, though. So this should still stand. It's just this does not. But I'll try and do that one later too. Now I know on the last one, I told you guys to make sure you look up cross product. I hope you guys did. Um, these are the two ways that I remember doing it. Um, so this one is just you added a place with the zeros, and then from there you kind of FOIL it out where you're like multiplying it all. And then from there you're like, okay, this one's zero, this one's times zero. And then you also do like the same cross the same. So then anything that's cross the same gets canceled out. And then your zeros get removed. And then from there you simplify, you solve for the crossings. Remember that's like if you're going this way, then it's positive. So I cross J is equal to positive K, while I cross K is equal to negative J, as we see here. It's negative. And then the other method that I've seen, so that doing all that gets you this. Another method that I've seen is you have your columns for IJK and then your phantom I to cross with K. And then from there you cross I with the J's, cross K with the J with the K's, and then you cross K with the I's. And so then this becomes K, these two become I, and these two become J, right? And then from there you simplify out into this, which becomes, reorganize it, gets that. In the end, they both get about the same answer, but I have like all positives here and then I have some negatives here. So I'm not sure which one is right. I want to say that this cross method is more proper. Okay. And then I said I was going to try and do this one, or at least walk you guys through it. I'm gonna be honest, I haven't worked it out yet, and I'm swamped, so I'm just gonna work it out through here. So you have your two balls. This one's at 0. They're gonna collide. After the collision, you should always have a before and after, by the way. After the collision, you have these two. This actually looks a bit more like this, maybe. But the x component should still be the same, but the y components will not be. No, wait, other way. X components won't be the same, because this one's going to be bigger. The y component will probably be bigger too, if you have the same. Yeah, it's not symmetrical. But kinetic momentum is conserved. Kinetic energy and momentum are both conserved, so both these stand. So you can make this equation. You can make these two equations. But you just can't use this assumption here. You have to solve them all for themselves. And take care. Bye.